Hey everybody, today we'll do another video and we will continue in the area of um, second order circuits, and it is going to be a kind of lengthy video because it's one of those that we have to find the initial conditions. We don't have them, so but the question reads as follows. So it says find the circuit. Okay, for the circuit in figure 19, 8.9, for the circuit in figure 19, I'm sorry, 8.19, find B of t, and I of t for t greater than 0, right? And then it says considered let's see what else. Okay, so we do, okay, consider this case, right? So consider these cases, right? So it says that R equal 5, R equal 4, and R equal 1 ohm. And this all are ohms, right? So they all are ohms. This guy is ohms, and this is 1 ohm. So all are ohms, right? So now, so I will just erase this because this is a problem statement, but I will just keep this one. We consider this case. We don't have a time, I guess, to do all the cases. It takes a while. So I will just erase this, and then write a circuit, right? So okay, so we consider that R is equal to 5, right? So we do in case R equal 5 ohms, right? And then, so the circuit in that case is right here has a 24 volt, right? So 24 volt voltage source. And then right here we have a resistor, which is the R, this R, right? That we consider right now. Then we have an inductor, and the value of the inductor is 1 Henry. It's 1 Henry. And right here we have parallel with that we have a capacitor, and this capacitor is 0.25 farad, and then we have, in parallel with that, we have a resistor that is 1 ohm. And then everything goes right here like that, right? So it's you know, So that is the circuit, and those are the values. So R in this case, we've taken this equal to 5 ohms, right? So now with that information, we need to start thinking about the circuit, right? So now, notice that the problem statement says something about t is greater than 0, right? So that means that we have a switch right here. I believe that's what it says. The switch was closed, but somebody opened it. And when somebody opened that, it broke the connection, and at that point, t is equal to 0. So at t is equal to 0, you have the case of, if you have some charge dissipated, it's still charged in the side of the circuit. If you don't have some charge that need to be dissipated, then but at t is equal to 0 is considered nothing. It's considered the circuit is still in what is called a steady state. Now, when t is greater than 0, right? So our goal is to find t, right, at when it's greater than 0 is when some in the system, if you take a capacitor that was connected to the voltage source, right, and you break that capacitor off, you disconnect it from the circuit, you will find out that the capacitor will have some charge even though it's having cut off from the circuit. Believe me, I've done this with a real life situation. Sometimes I had to disconnect a circuit board one time that it was connected to a circuit and disconnected, and a few minutes later I accidentally touched the board, and of course there was still some electricity stored, or some charge stored in the capacitor. So it takes a while for a capacitor to discharge. Sometimes you need to charge that capacitor in order to get fully discharged, but that's another thing. So what I'm saying right now is that when this is at the moment that t is equal to 0, it's kind of nothing happened, right? But at the moment when t is greater than 0, then is when this get isolated, and then we have a loop right here, like that resistor is being cut off, right? Assuming this is the load, but we still have some current around this resistor, and the resistor, and of course any element. In this case is the capacitor, but we don't have. If it's a DC source, then we assume that it's going to be open, that the voltage across this is going to be across in this, right, in this capacitor. But in an AC source, it's a totally different thing, right? But right now we're dealing with this. We're dealing with the whole system, not only with this case. So that's why I wanted. But I wanted to show you that when you have a capacitor in DC, because the capacitor in DC doesn't let any current go through the capacitor, right? If it's connected in the DC source, it will act as an open. So whatever voltage you see over here is what it's going. You will see at the capacitor if it's in DC, right? But the problem statement doesn't state whether it's in DC or AC source, right? But anyway, so let's start doing this, right? So we start by taking this information, right, is equal to 0, right? At t is equal to 0. So now at t is equal to 0, that means that at that moment this is still, assuming that it's still closed, right? It's nothing at the moment that is done yet. We assume that this is connected to this guy, right? So we'll consider the current going around this and thinking about this have been open. This has been charged for a long time, right? So the capacitor is acting like an open circuit right here, and it's going, the current is going around this. If at the moment that the person hit this and the time start increasing is when things will happen and things will get isolated in the circuit. In this case, it's going to be that resistor. But so now let's consider the case where it is simply like this, right? So let's consider the case that this is disconnected, right? Connected like that, right? Nothing happened yet, right? Okay, so we will consider this case, but I'm just trying right now, right? So, but anyway, that's the switch. That is somebody open it. Okay, but we will assume that it's closed, right? So now, so to find the current, right? So we need to find the current B at time is equal to 0. Okay, so we know that at that moment, at time is equal to 0 is steady state, right? So it's 24 volt. Now I at t is equal to 0, right? At t is equal to 0, then it's going to be voltage at t is equal to 0. At t is equal to 0, which is steady state, over what? Over R, right? R, the one that we had, the one that we use, right? The one that we use, 5, right? Plus the 1 ohm that is here, right? So now at that moment, so what we do is we put the 24 volts in there, and then we have 6 in the bottom, right? Which is going to be 4 amps. So that's the current going through that circuit at that moment. That is the total current, right? Now, so that is in that condition. So we found one condition already, right? So if this marker was working, would be nice. At t equals 0, right? Now I of 0 is equal to 4 amps, right? Now, if you think about it, so we got a current going around this loop, right? Which is going around that one, which is technically going around that resistor. So now think about this. So now, if you take a voltage meter, and you measure the current around this, it's going to be the same, right? It's going to be the same from this point to this point. Why? Because it's in parallel. So we can say that. B of capacitor at time equal 0 is equal to what? Is equal to R. Is equal to the equal to R, 1 ohm, right? Which is that one, times what? Times current, which is going to be equal to 2 times 1, which is equal to 4 volt. So we found this condition too, right? So at t is equal to 0, voltage at t is equal to 0, also the capacitor is equal to 4 volts, so V of C, right, is equal to 4 volt, which is also equal to VR, right? VR 1 1 ohm is also 4 volt, right? Because they're in parallel. That one, this one, and this one is in parallel. Okay, so now that we have that, so we have that, right? So we have that. Now let's do something else. Let's find the values to analyze the circuit, whether the circuit is dampened, under dampened, right? Over damp, critical damp. Those cases, we need to work that out. Now, so notice that in the case of we need to find alpha, right? We need to find alpha, right? And so notice that a moment that is, even though this is considered in parallel with this, right? But at the moment where this circuit is open after T is greater than 0, this is considered in series. So after T is greater than 0, this is considered in series. So it's going to be looking around over here instead of going around the circuit. So now we're using the formula that is called R over 2L, right? Because this is in series, this is series, right? And then if it was in parallel, we find that we will use alpha is going over R over 2L times C. This is for parallel, right? So now, but we dealing with this only at the moment. So we do this. So we know that alpha, we take in the case of when it's 5, so it's going to be 5 over what? Over 2 times what? Times the L, and the value of L is 1 Henry. So that is 1 Henry, which is equal to 5 over 2, which is equal to 2.5. Now let's do the omega, all right? So omega is for both, right? So omega is for both, right? Or if the either parallel or parallel. If the inductor is in parallel with the capacitor, or they're both in series, it doesn't matter. So we use this one. It's called the square root of LC, or LC. 1 divided by square root of LC, which in this case, omega is going to be equal, omega naught, right? It's going to be equal to 1 over the square root of 1 times 0.25, right? And when we do that, simply we get, making sure that when you do dealing with this stuff, it's always good practice to use a calculator, because even though you can actually do some of this stuff in your head, but okay, so yeah, so it's 2. So it's a good practice to use the calculator for this type of things, because you might want to say, oh, I know the square root of 25 is 5 or whatever, but this what if it was 26? You cannot really approximate stuff like that in your head. I mean, you can, but you're not gonna be as accurate as using the calculator. Okay, so now we know that this is 2, right? So now omega is less than alpha, which omega is less than so have this case. So we have that alpha is greater than omega, which means that we have over-damped system. Right? So over-damped. So so now what we are going to do, so we found that, right? So we found that there is an over. Okay, so we have in this case that it is an under-damped system. It's over-damped system. It's over-damped system, right? So the natural response of the system is over-damped, right? So now let's try to do so. Okay, so now let me write those values. So we have omega naught is equal to 2 and alpha is equal to 2.5. Okay, so let's just keep doing this. So, okay, so now that we have this, right, we need to find what is called S1, comma, S2, which normally is negative alpha plus or minus alpha plus or minus alpha squared plus or minus omega naught squared, right? So in this case, so we do S1 and we take the positive sign of that, right? So it's going to be negative 0.5 plus alpha, which is 2.5 squared plus 2 squared. So when you square that, right? So and then this is going to be equal to the square root of, so minus 2.5 so minus 2.5 plus 6.25 minus 4, right? Minus 4 is equal to what? When you square that, 2 is equal to 4. When you square that, it's equal to that. So basically, now you know that this guy is going to be under the square root. It's going to be 0.5 plus the square root of 2.25, right? So now you take the square root of that, right? So okay, so it's 1.5. Right? So okay, so now we have that this is technically what is under here. So this is not complete yet, but still need to add negative 2.5 plus 1.5 is equal to negative 1. Okay, so we have that S1, right? So S1 is equal to negative 1, right? We have the first value. Now let's do S2 is equal to minus 2.5 again. Now we take the negative part of that, which is going to be equal to, and again the values are going to be the same, right? It's going to be the same inside there. So it's going to be when you do the math inside, it's going to be the same thing. So it's going to be 6.25 minus 4, right? And then when you do this mathematics over here, it's going to be S2, which is negative 0.25, right? Now be careful because we're taking the minus. So that inside here end up being the same thing, but it's going to be negative 1.25, which is equal to negative 4, right? So that is S2. Now, so we have S1 and S2, right? So now we have S1 and S2, and so I can write right here. So S2 is equal to negative 4. Right? So we have those values. Now, now we have some. Now what we can do, right? So what we can do now with this value is we need to write an equation, and the equations are technically these values, right, multiplied by a certain t is with exponential. So basically it's going to be b of t, if it's a voltage like b of t, right, is going to be equal to what? It's going to be equal to some constant A1 in this case, right, because we have another overdamped case. So E to some at some t, right? Some st, s1t plus a2e to the s to t, right? But in this case, we know what is s1 and s2 is. So basically, we just replacing that guy by 1, and then we replacing that guy by 4, right? So now we find that this is, right, the one of the equations that we can use, which is technically you can actually, because at that moment we leave it as it is, but you can actually write this constant out, because these are arbitrary constants. But in this case, we'll leave it as it is for right now, because we still have to do something, right? So this is just t, and that is just 4, right? Okay, so now negative 4. Now let's do this. So the next case is going to be assuming that we have the value of this, right? Assuming that we have the value now. Remember that we consider the case where it's a steady state. So in order to have a steady state, that means that you have the constant voltage already at time is equal to 0, right? And if you remember from algebra, when x equals 0, you can have a y value on top, and that is representing a constant value at that time t is equal to 0, because technically the voltage at that moment is whatever the constant is, right? So I'm not going to have a time to explain it right now, but assuming that this is steady state, so that means that at that moment that was already voltage when t is equal to 0, and this is already voltage in the system. So what we can do here is the following. So we can say that V of t, I am going to rewrite this the same. It's the same thing, just adding the voltage, which is going to be equal to BSS, which is the steady state voltage, that voltage right there, and then plus A1E to the T to the negative t plus a2 e to the 4t. Now, what is this voltage? So V of t is equal to 24 volt plus a1 e to the t plus a2 e to the 4t. And that will be the equation that we will be considering. Why? Because we had a steady state voltage already. Now we can actually start working with this. So I need some room here. So okay, so we know that S1 is equal to -1 and S2 is equal to -4, right? So now we know that the voltage in this guy, right? So we have one of those conditions, right? We have one of those conditions already. At the capacitor voltage and the resistor voltage is the same when t is equal to 0, right? So what we can do now is that, assuming that this side is 0 at the moment, and leaving that in the other side of the system as a steady state, we can actually use the condition of voltage is equal to 4 volts at t equals 0 and replace that right here, and then solve this equation, right? So we can do that like this. So instead of saying, we say V of 0 is equal to that one, right? So equal to 24 plus a1 e to the t negative plus a2 e to the 4t, right? Now this guy right here is 4 volts, right? This right here is 4 volts, so 4 equal to 24 plus a1 e to the t plus a2 e to the 4t. Notice that I can actually get this in the other side, and it's equal to -20 a1 e to the t plus a2 e to the 4t. Now that is one of the equation, another equation that we actually can use, right? After some time equal 0, we start working on that. Okay, so with the change, using the condition, we use that to manipulate the equation. Now we have this. Now, and think about this like something that is changing but not having a theoretical change yet, right, in the system. So now what we can do now is the following. So we can take the derivative of that equation. So we can take the derivative of that equation, right? And say that at the moment when, okay, so now, okay, so now if we take the derivative of this, right? If we take the derivative of this, so take the derivative of this whole thing, equation, right? So we say that dv at 0 dt, but this guy, right? So was technically at the moment it's taking the derivative of this, right? Because this technically is that, so it's 4. Oh, so it's 24, right? Plus a1 e to the t plus a 2e to the 4t. When I take the derivative, this goes away, right? And that comes in front, that comes in front, and I can say dv over dt, right? What changes is 0 in this case. I mean, we know that it was 4 volts at the moment. So at that case, we can say that a1 e to the t minus, that comes in the front, 4 e to the negative 4t, and that is the derivative of that equation, right? Now notice that we can actually use this equation to find out the rest, right? So now, thinking about this, right? Think about when this guy at time is equal to 0, we have this change, right? But in this case, we have the derivative. What else we can do, right? What else we can do? What we can do is to say that dv dt at 0 when the current, okay, so we can say that I of 0, which we know that is 4 amps, right, is equal to C, right, C dV over dt. The change in voltage on the change in time of that capacitor when at time the current is at 0 time, well, we know that. We know that in this case is 4 amps, right? So 4 is equal to C over the times dV over dt. Now manipulating this equation is equal to what? Is equal to dV over dt is equal to 4 divided by c, 4 over c, right? Now we know the value of c, right? So now what we can do now is the following, right? So now what we can do is the following. So now notice also that at the moment of this, it was also 4 volts. You can take it both, you know, this is the same. It's going to be 4 volts at that point, right? So now look at that. So dV over dt at 4 over 0.25, right? And it's equal to 16, right? So 16 volts, right? So this is a process, but it's I think it's worth it going through this pain because it makes a lot of sense after you start doing this. So now we know that is 16, right? So that is 16 volts. Now we can use the 16 volts in order to get the rest, right? Okay, so actually you can use, well, yeah, I mean this is proportional. dV dt is equal to, at this, right? They're really okay. So okay. You can do it like this too. So it's happen to be the same, right? right? So 4 volts is equal to that, divided by that is equal to, yeah, technically it's equal to 4 over 0.25, which is 16, right? So we did this right here. But anyway, so let's keep doing this. So this is a different condition. Now we have another condition, right? So now that at the moment, so we know that, okay, so dV over dt, okay, so it's equal to 16 volts. Now notice that we see the increase in voltage, right? So you see like some changes are going on, right? As the time passes. Now what we can do at this moment is simply use the equations, right? So now at this point we can use this condition and this condition that are both in voltage, right? So we can say that this 16, right, is equal to A1 plus A2, right? Now after we took the derivative, we had after we took the derivative, we had this guy, right? We had this guy, but this guy can be written as the following. So just without this mess, so it can be written as actually. So this is dV dt, right? So now what we can do is replace this, right, by this, and simply write it like this. Substitute the dV dt right here, right? This is the value, so I am substituting right here. So it's going to be negative A1 plus, okay, a negative 4A2 in negative, right? Now, what was the other equation that we had, right? After we manipulated the first change when t at t was equal to 0. Well, in this case, with this one, right? So I can actually write that, and it's going to be negative 20 volts is equal to what? That's a positive A1 plus A2. Now, I have a system of equations that I can work with, right? I can add this and add that and add this, right? So I got negative 4. Negative 4 is equal to what? Negative 4 is going to be equal to negative 3A2, right? Now notice that what I'm doing right now, I'm trying to find values. Okay, if I have a room, find A1 and A2. That's what I'm trying to do, right? So now, because we need all these values in order to have an equation, right? So now let's get this done. So divided by 3, trying to solve for A, right? Notice that there's a negative, right? And there's a negative, of course, that cancels out, and I am left with A2 is equal to 4/3. Okay, 4/3. So A2 is 4/3 now, right? So we found that A2 is equal to 4/3. And I need to find A1. So how do I find A1? So I guess, going back to the high school times, substitution, all that, we can kind of think about that stuff, right? you can use any of these equations in order to find this, right? So I'm going to be using probably that one on top, right? So negative 20 is equal to negative 20 is equal to what? It's equal to A1. I know that this is going to be A2 is going to be this one. So when I do that, so A2 is going to be equal to this one. So I'm trying to find A1, right? So A1 is equal to, and then 4/3, right? Move this to the other side. What do I get? I get that A1 equal to negative 20 minus 3/4, right? And then when I find the common denominator in this guy, right here, no, actually, the opposite is 4/3. So the common denominator in this guy right here is going to be, this is going to be equal to A1. So A1 is equal to negative 60/3, right? And then minus 4/3, which is going to be equal to negative 64/3. So that is A2. I'm sorry, A1. That's A1. So now we have A1. A1 is negative 64/3. Okay, so now we have the two values. Once we get the two values now, right, we are ready to write the first equation, right? We just substitute that, those guys over there, right? So, might have to get rid of this. Yeah, we don't need this. We don't need that. Okay. So, okay, so now we have that guy, right? So we substitute it in this. So B of t is equal to what? Is equal to negative. But remember that we still consider the initial conditions, right? So that guy right there. So it's going to be 24 volt, right? And then plus this, right? But remember that this guy was a negative, so A1 is a negative, so it's going to be negative 64/3 e to the 4t. I'm sorry, just to the t in this case. And then 4/3, and then plus 4/3 e to the 4t. Notice that I can actually factor out this 1/3 out and leave in whatever factors out with this. So it's going to be 16. So it's going to be B of t is equal to 24 volt, right? Plus, it's minus. I mean, you can factor a positive. Factor a positive and leave the negative 16 inside. So factor plus 4/3 a negative 16 e to the t plus e to the 4t, and that is one of the solutions, right? That is one of the solutions that we're asking for. At time is greater than 0. At time t, right, greater than 0. So now for the current, they're asking for the current, right? For the current we do similarly, but with the exception that we don't have to do too much of this crazy stuff. We need to simply we noticed that at the capacitor was 0.25 farad, and the current at that, when it's considered at the steady state, right? It was 4 amps, right? So we can use that. We can use that, right? And then, so we can use that I of t is equal to that, right? So I of t is equal to dV dt, right? At 4, okay, at that moment, right? So I of t is equal to c dV dt. Now, taking that as information, so what was the derivative? We can actually use now this guy right here, right? And we can actually use that equation by multiplying the value of this guy, right? We can use the value of this guy multiplying this equation right here, right? And then replacing everything. So we can do that. It's going to be kind of messy, but okay. So we can do right here is that rewrite this and multiply everything by the value of the capacitance, because the value of the capacitance is right in front of this dV dt. So we can actually multiply this equation, right? So A1, right? A1 e to the t times 0.25, right? And then obviously, okay, so let me just put this. A1 is a negative, right? It's negative. So e to the t, right? And then also A2 is negative 4. So it's going to be 0.25 times 4 e to the negative 4t, right? When I do that, this simply does that doesn't change. This changes to 1. So this is going to be equal to negative 0.25 A1, right? A1 e to the t plus that, right? But remember, right here, you need to be careful because I am dealing with A. I need to have an 8 over here. So it's going to be 4. So in this case, it's going to be 4. It's going to be 0.25. And then, okay, let me do it right here. So, negative 4, A1, e to the 4t. Okay. So now when I multiply that, that becomes 1, right? 1, 8 is A2 e to the 4t. Okay, so now what we can do is the following. So just replace the value of A1 and A2, right? And then right here, so this is the current, but remember this is the current. So we're trying to find I of t now, right? So now I of t is equal to that. Now, when I replace that, it's going to be after I replace this, right? So let me just do a step by step. I might have to erase this. erase this. This is getting too clustered. Okay, so this is the equation, the little equation that we're dealing with right now. Just make it. Okay. So now I am going to replace, right? I'm going to replace I of t. I'm going to replace that 0.25 times negative 64 thirds, right? E to the t minus that guy, right? And then this one is going to be it is going to be a negative. This is going to be negative. So this is a positive, right? But the value of that was a negative. I'm sorry. This is a negative, but the value of that was a positive. So it's positive 4 thirds e to the 4t, right? Now when I do that, this is 4. When I do that, this guy right here is equal to 64. So 0.25 times 64. So it's going to be equal to positive 16 on top. So it's going to be 16 over 3, right? And then e to the t, right? And then right here, I got 4 thirds e negative to the 4t. Notice that I can factor out right here, right? I can factor out this guy right here. I can factor out 1/4 out, and that leaves me with 4 inside. So it's going to be equal to 4 thirds, right? And inside is going to be 4 e to the t, right? And it's going to be equal to simply that. So it's going to be e to the 4t, right? And that will be the answer for that. So now, as you can see, now you can actually close this right here and call that amps. If you want to be more specific, because this is the current, which is equal to I of t. All right, I of t is the current. And the voltage, we found that out, that is this guy right here. We can call that V. So as you can see that is the answer for that problem. That's the voltage, and the current is that one. So I'm just making sure that this looks like this is the current, right? So we're dealing with 2 different things here. So those are the 2 solutions for this. So it's going to be that one and that one, right? Final solutions. So I hope this helped. I'm not gonna have the time to do the other cases because it takes too long to explain this stuff. Thank you for watching. I see you in the next video, and just another reminder, this is a Christian home, so we learn something every day because Jesus is good. And I hope you like this video, and I see you in the next video. Thank you for watching.